So let's get started. So today we're going to be talking about streaming algorithms, and so just a quick look at the schedule. Right here, we're actually going to try and do essentially 2 lectures at once because of the snow day. This is the day that kind of is getting the most compressed. So then on Monday next week we'll start into regression. I think giving some insight into this will be important for like a bunch of your projects. So hopefully all of you turn in your clustering homework. I think now you've done kind of the 8 assignments, you've probably done 3 of the hardest ones already. Okay, so hopefully the load will start getting much lighter in the course of the assignments. Hopefully you're shifting some over to your projects. You should have gotten some feedback on the data collection reports, so maybe just recently, like just a few minutes ago possibly. So I'll talk more about that next week, Monday as well. I kind of want to get into the actual material because we're trying to do a bunch of things at once. Finally, the frequent items homework is going to be due in 1 week. It should be, I kind of previewed it at the end of last week, and then you'll have the stuff you need today to work on that. It should be, I think it's dramatically simpler than the clustering homework is the feedback I've gotten. So, so that should be okay to finish in the next week. And then hopefully we'll get feedback to you on that assignment in time for the midterm. Also, I'll talk about this a bit more next week on Monday. But that's coming up. I posted some stuff on Canvas about this in response to a question as well. Okay, so that's where we are in the schedule. Oh, and then there's spring break. Great. Good. So getting into this quickly. So we're talking about the streaming model, and just to kind of quickly review, this is a model for dealing when you have a large amount of data, and you want to know how to deal with it. Kind of traditional, even polynomial time algorithms, maybe even almost, like a lot of the clustering things you might have been looking at, don't scale very well to data of just enormous size. I mentioned there are basically 3 general ways of dealing with this. One is essentially sampling. This could be random sampling or maybe other ways. Then there's the streaming paradigm, which we're talking about today, where you try to basically make one pass over the data. And most of the time in dealing with the data is then just bringing it off of disk into the computer's memory. You make one little kind of look at it, and you update some sort of summary statistics, essentially, of what's going on. And that's the main model. And then we'll mention this other one later in the semester about MapReduce. And this is when the data is so big, it doesn't just fit on one hard drive, but it fits on multiple hard drives. But again, in this case, it should be fairly static, where the streaming model might deal with when the data is you're continually updating your data over time. So that's another view of this model. Right, okay, so let me just write down from, I think this is important, the main notation in the streaming model. Okay, so the idea is you're given a data set A, and we can think of these as A1, A2, J up to M, and these are given to you in order, right? So you're kind of reading these in order, and you basically want to read through them once, kind of like thinking you're doing, the only way you're accessing the data is through a for loop on this data. You know, in your homework, that's how it's going to be. If you're on a router, it's just being kind of, there's data kind of flowing in through a pipe, and you're just dealing with it as you can, right? There are other settings from a, if you're a computer science background, just think of it, you can access it through a for loop, and that's how you're accessing it. Okay, in order, and even an adversary often can decide the order, right? So it may be all of one type is at the beginning, all of a different type is at the end, but you want to say something about the whole data set. Okay? So think if you're doing clustering on this data, and all of one cluster is at the beginning and all of another cluster is at the end, that may be more difficult than if they're all mixed up, right? So you have to think about these different scenarios because you know, if you want to do packets on a router over time, the distribution over the course of the day might change. Okay, so now we'll say, to simplify our life, we'll say each j, each aj, each element is going to be inside of some domain. Okay, these could be these IP addresses. They could be these kgrams. You're scanning over a document, creating different kgrams. You know, they could be a representative of like a different user ID or a search query in some website, but we're just going to represent them as some set, right? There's some set of size n, okay? And I don't necessarily need to know how large n is exactly, but maybe get some upper bound. And basically the idea is that m and n are very so large, where I can't store something on the order of m and n. M is the size of the stream. N is the size of the domain. Think all possible IP addresses. I don't want to store something for every IP address. What I can do, I have space that I want to use, which is going to be something like log m, you know, plus log n. This times some sort of constant. All right, so I want to think in terms of log m and log n. And the right way to think about these things is that log m, this is like a counter. I can basically, in log m space, log m bits, I can keep a count of how many of something I've seen. Because there are m things, that's how many bits I need to keep a counter. And log n is like a label. To write down a specific IP address, I need log n bits. But instead of writing all IP addresses, requires n space, right? Something for each of them. But if only log n bits, I can write down the specific one IP address, right? So think of the space on the order of the log of these sizes. It's kind of the thing I want to aim for. And there's going to be some other constant C I wrote off to the side here. I'm going to kind of sum multiple of this, right? So, but the base thing should be log m and log n in most cases. So there's some variations of this model when you're dealing with streaming stuff on graphs. It's not quite this way, and the trade-offs aren't as big. And there are different versions of these models. But the problems we'll discuss, we want to get down to the logarithmic of the total sizes that we're dealing with here. Okay, so an exponential improvement, basically, in space. Okay, and so now I want to introduce one new model we didn't talk about last time. And so this will help, and so this idea of the frequencies, okay, and so I want to write down the frequency of an element j, okay, is going to be equal to, it's the number of times the jth element in the domain has occurred. So let's say that this is, so for all elements of the stream, so I want to look at the set of these that AI is equal to j, and this cardinality of this, the size. Okay, so this is so the number of times I saw the jth IP address on the router. the number of times I saw a specific word in some large corpus of text. So if I'm keeping a counter, right? So I can, basically this, to keep track of one fj requires one counter, which is log m space, okay? And if to keep track of the value j requires one label, which is log n space. Okay, so these are kind of things I can keep j and I can keep the count associated with it. That's something I can keep track of. Okay? And then there are kind of some general summary statistics on top of this that people care about. F0 is going to be the sum over j of fj to the power 0. And this is the number of distinct elements. Right, so if I take something to the power 0 and it's 0, that's still 0. Otherwise, it's going to be 1. So I'm just counting the number of distinct elements. F1 is going to be fj, this sum over j of fj to the power 1. This is just basically is m, the number of elements. Okay, I can solve this with one counter. Right, just keep one counter. It takes log m space. There's actually a classic way you can approximate this with log m space. We're not going to talk about that in class, but that's actually, if you just want to keep track of a counter where this is super, super big, you can actually approximate fairly well with log m space, just a counter. There's this really cool paper called hyper log, which kind of shows how to do this. Okay. And then something else that will come up possibly at the end of the lecture today is fj squared, and so this is the second, what's called the 0th frequency moment, the first frequency moment, and the second frequency moment. This has to do with like if you know database literature, this is like approximating like the join size. If you do a join over things, it's about how large it's going to be. So the join size, it should be, and then you often want it, you write the square root of this here. Okay, so we're going to look at some algorithms today, and they're going to write bounds in terms of these two quantities. So I just want to write them up here. This one is actually in most data, after you take the square root, this one tends to actually be much smaller on most data. If it's a fairly non-uniform distribution, like there's a lot of some item and very zeros in a lot of other places, this one's typically much smaller. Okay. Okay. So these frequencies are going to be something we're going to be talking about, and it's not because it's the only thing you can do in the streaming model. Like people have studied just about any concept we've talked about in this class. How do we do it in the streaming model? We're going to talk about these frequencies because it fits very natural. The algorithms are kind of short and beautiful. You kind of get the concept of what's going on. And actually these basic algorithms, it's extensions of these that deal with these frequencies that are actually the building blocks of these more complex things for, say, dimensionality reduction or clustering or classification. And we'll see one of those extensions after spring break for dimensionality reduction. We'll use something that looks like a streaming algorithm that keeps track of these frequencies, and will end up being used for taking very high dimensional data and in a streaming manner reducing it to low dimensional data. Okay, so they're kind of abstract, but they're kind of the basic building blocks of what a lot of people do in this streaming model. Okay, so most of this we talked about last week Wednesday. We looked at this majority problem, and I basically wrote up what was in red on last week on Wednesday. So this is, think of, and I've rewritten in black here what is in this using these frequency counts, right? So let's say I want to know, is one of the IP addresses, let's say I'm sitting on a router, okay, and I want to know if one of the IP addresses is on more than half of all the packets I've seen. Okay, so if it's on, that means in this language of the frequency counts, is there some Fi, some frequency count, which is greater than n over 2, or this should be m over 2. All right, so greater than m over 2. Okay, so is there some Fj, let's keep this consistent, okay, so is there some Fj where the frequency count is greater than m over 2? So that's the same question. And if so, then I want to report this j, right, such that this is true. So then tell me which one this is. If there's not, then I can guess. Okay, then I can return any value j inside those limits. Okay, so this is kind of, if someone won an election over these packets, I want to return it. If no one won the elections, then everything is fair game. Okay, and we described how to do this very, very quickly with one label and one counter. Solve this specific problem, and I needed to have this thing that if I didn't satisfy it, then I could guess. Okay, otherwise this isn't going to work. Okay, and so with one label and one counter, does anyone remember what we said last week? How do we solve this? What's this basic algorithm?
Isn't it you just like count the you just keep track of the number that has like the most occurrences, right, and then return that at the end of the loop?
So, but how do I know which one has the most occurrences?
You keep a count, right?
Right, so I keep a count, and how do I know which? So you're saying I keep a label for one that has the most occurrences, and I keep a counter. If I see that label, I keep a counter.
Yeah.
But how do I know which label to keep?
Well, you would count the number of occurrences for that specific label, and then if you see a different label, then you decrement that counter.
Ah, okay.
Yeah.
Good, right. So I start by making a guess, right? The first label I see, I'm guessing that this label is going to be the one that's occurring the most. And if I only see one so far in the stream, then that one is, if the stream stops, right, then that one is a majority, right? So I keep a label and a counter for this one. If I see that one again, I increment the counter, right? If I see a different one, then I decrement the counter. And if the counter gets down to 0, then I swap the label. Okay, so and this is the whole algorithm. I've wrote it up here as a for loop. Okay, so I have one counter, right? So I've got, this is a counter, and this one is a label, right? And I set the label to the empty set initially. Okay, and so now, right, so I just write this for loop that goes through here. Okay, if AI equals the label, right, then I increment it, right? So this is my increment. If it does not equal the label, then I decrement this counter, right? And then I have this special case here that if the counter drops below 0, which happens on the first time because I decrement it because it was an empty, it didn't match initially, then I reset the counter to 1 and I reset the label as the thing I'm seeing right now, right? And so this is the whole algorithm, okay? And so it satisfies this property that I wanted. It satisfied this majority kind of this task, okay? And so the right way to think about it, so actually I'm not going to analyze this. Let's describe the next version of it, and then we'll think how to analyze it. I'll change just a little bit, and we'll extend this, and then I'll explain kind of a more general version why this actually works. Okay, but hopefully you kind of get the sense that if something occurs more than m over 2 fraction of the time, I have to keep incrementing the counter, and then there aren't enough of the decrements left in order to get rid of it. You want to make sure the argument holds that if that one doesn't occur at the beginning, that it flushes out everything that was there before it. But you can kind of, at least without a formal argument, you probably intuitively kind of can see where this works. Okay, for a generalization of this, I'll provide a little bit more cleaner analysis. Okay, so now I want to kind of extend this to what's called so the heavy hitters problem, okay, and this is kind of it's essentially a special case of what's called the frequent items problem. Okay, so the heavy I guess the term heavy hitters came first, but and it's a little bit more catchy, but kind of frequent items is a little bit more general problem. Okay, and so what I want to do is I want to now report all Fi which are going to be greater than m over k. Okay, so k is now parameter and often going to be something larger than 2, right? If k is exactly, if k is 2, then this is basically this roughly the same as like the majority problem. This is, I only want to care about reporting things which are greater than m over 2. That's the majority problem, and I can make some bad guesses so otherwise. But I want to do something a little bit stronger. So I want to actually say, I want to report, okay, so this is basically the heavy hitters problem. The frequent items problem is I want to, for all j so for all j inside this domain, I want to have access to an fj hat, okay, an approximate version. This is an approximation of the frequency, and it's going to satisfy something like fj hat is going to be less than or equal to fj plus m over k, and it's going to be greater or equal to the true fj minus m over k. Okay, so this is the frequent items problem. Okay, so for all values of j, right, I said there are n of these. N is too many things to keep track of. And I want to do this in small space. But I want to be able to report some approximate fj hat that satisfies some property like this. Okay, and so in some cases, actually, we're going to actually make something stronger. So we're going to talk about one algorithm that is where it's going to just have this guarantee. This is going to be the Misha-Gries algorithm. And we're going to talk about another algorithm that is just going to have this guarantee here. Let me draw this a little bit better. Right, so it's not going to have the error on the bottom side, and this is going to be the count min sketch. Okay, where I'm in one case I'm never going to overcount for the Misha-Gries, and in the count min sketch I'm never going to undercount. So I'm always going to give an estimate which is too big, or always give an estimate that's too small. And then maybe, hopefully, we'll get a chance to talk about the count sketch, which will give a bound that has error on both sides. Okay, and there are advantages, different advantages to all these variants, and we'll kind of discuss this. Okay, but I want to be able to give an estimate for every value j. Okay, so first of all, like, how could this even be possible? Right, if I want my space to be like not depend linearly on m or on n, right? If I just kept all the items, right, that's m of them, I could just look this up. If I kept a counter for everything, I can just use the counter. Like, how can I do this?
We keep like an LRU cache of like the most popular elements, and then each time we see an element we haven't seen before, we evict like the least frequent thing in the cache. And then instead of keeping like the hill valley plot counter, each thing in the cache has like a counter for how many times you've seen it in total in the cache. And then it's possible that you'll see something early on, and it'll get evicted. But when it gets back in, it'll have a count. It'll be somewhat close or an approximation of the value of its total frequency.
Yeah, so this wasn't quite answering the question, but so what you're saying is you want to do like an LRU cache, right? Except keeping the high frequency things. And so what you've almost described without a little trick that makes it sure that you don't have your adversarial patterns is what's called the space-saving algorithm, which turns out will be isomorphic to the Misha-Gries algorithm. You can take one and convert into the other one. But there's one trick you need to make sure is when you evict something and you replace it, you need to update the counter in a special way. So this is roughly the right idea. And so what you're saying is only the things which are very frequent are interesting, right? And so in particular, there are two answers to this question I asked about how do we keep track of all these approximate counters when I could ask for value of j, there are n different values of j, and how can I return an answer for all of them? And your answer is basically, well, if it's not in the cache, I can return like 0, it turns out, right? So what I can do is if something is not in essentially my cache, then I can return 0, and because I can't have that many frequent items. I can only have so many of these things which are frequent. The rest I can actually approximate by 0, because if I take the true count and I subtract m over k, that value will be less than 0 for most of them. Right? So that means I can approximate most of them by 0. So I keep track of some number of labels and counters. And for those, I return an interesting estimate. For everything I don't keep track of, I say my estimate is 0. Okay, and so this will be kind of the pattern of the Misha-Gries algorithm. The space-saving algorithm, which is a little bit closer to what you described, actually keeps some lower bound, that one always upper estimates everything, and it keeps some lower bound, and anything not in the cache, it estimates like this lower bound value. And so, but you can show that is never too far off as well. So that's one answer. The count min sketch will do something completely different. Okay, it's going to somehow keep some data structure that you're going to be able to ask queries of. It's not going to be just a fixed set of counters and associated labels. It'll be more complicated. And you can ask a query for the value for j, for any value j, and it always returns you an answer. And it's guaranteed to have this approximation guarantee. Okay, it's kind of this magical data structure that you keep throwing stuff in, and it has a fixed amount of space. And that will come up with it. It's not like using a cache. It's kind of like throwing something into. It uses hash functions. Okay, so and we'll come to that second. All right, so let's. All right, so is this any questions on this or? Almost a question?
Sort of. So that the balance that we have give us like a range, right? And so you can have like k bins, right, of the range of m.
So think of, I'm going to control that. So m is the total size of the stream, and think of k as something that gives me, the right way to think about this is to set, yeah, so this might be a little intuitive, so set k equals to something like 1 over epsilon, and so then this means that m over k equals epsilon m, and then you can think of epsilon as equal the percent error. So if I set epsilon at 0.01, so epsilon equals 0.01, this implies 1% error on the counter. Okay, and so this also means that k needs to be 100. So if k is 100, then I get 1% error in all of my counts. Right? If I want 10% error in all of my counts, k is equal to 10. Right? In your homework, I think you'll set k equals to 10 for these algorithms. And you'll get 10% error, which is not really realistic, but it's a little bit easier to work with. You can try setting it larger and see what happens. But I think the data will be too easy for that sort of situation. And so if you set k equals to 1,000, then you get 1/10 of 1%, so something like that. So okay, and one of these algorithms will be basically only slightly more complicated than the majority algorithm on the previous slide. The hard part, and this is what I want you to do for the homework, you'll implement them, they're very simple, but you need to kind of interpret this error bound. And you're going to get an answer, and you're going to have to say, okay, what does this answer mean? Okay, and so that's how you're going to have to think. And it's basically doing algebra on this equation. Okay? All right, so let's go the details of the algorithms. Hopefully they'll make more sense. I'll write down the special forms of this for each algorithm where they either only have one-sided error, and we can talk more about this. Okay. Okay, so the Misha Gries algorithm for the heavy hitter problem. Oh, Mishra, sorry. Okay, so this is an algorithm that's going to essentially have this idea of a cache. Right, so this cache is a good way to think about it, and it's going to have k counters and k so k counters and so k labels. Okay, and it's going to solve this frequency approximation, this frequent items approximation problem. Okay, and it's going to be, we went through this majority algorithm quick because it's essentially going to be an extension of the majority algorithm. Okay, so I'll show you the pseudocode and we'll go through that, but I think it's easier to actually kind of try and derive this algorithm. Okay, so if I have k counters and k labels, so basically I'm gonna have k. These are gonna be basically my k my k guesses for which items are going to be fairly frequent. Right? So I can think of having, and so actually we'll discuss it with actually k-1 counters and k-1 labels. And the analysis will go through when I use -1, and we'll see that way. But we can describe it with k, and then the pseudocode uses k-1. Okay, so let's say I have k counters and k labels, and so think of these as counter 1, counter 2, up to counter k, and then I have a label 1, label 2, up to the label k. Okay? And so now, what should I do when I see a new element that matches one of my labels? Right, so I'm going to have a for loop over this stream, and so if I say aj equals some label, say J prime, right? It equals some label, then what should I do? Right, so I'm going to increment the associated counter. So I do an increment, okay? Okay, now let's say else, and then there are going to be two cases in the else statement. If this is true, and some Cj prime is equal to 0, right? So now there's some counter which is equal to 0, then I should do what? Right? Then I'm going to set label J prime equals to AJ, and I'm going to set the counter J prime equals to 1. Okay, so if I basically have a free counter, this means it's empty, right? So this is an empty counter, right? If I have an empty counter, then I can use that counter, right? I can take over that one. I can update its label and set the counter as 1. I've seen one thing of that. Okay, and so then kind of the tricky part is if there's no counters at 0, right? None of the counters are empty. So then what should I do? Yeah.
Decrement all of the counters?
Yes, right. So so this is the right answer. So if all of the counters are being used, then I'm going to decrement all of the counters. So for all J prime in K, that's how many counters I have, I'm going to set J prime, I'm going to do a minus minus. So I'm going to decrement it. So if everything's full, I'm going to decrement all of the counters. Okay? So this is the whole Misha-Gries algorithm. And then if I ask a query, what's the frequency for item J? I see if that matches a label. If it matches a label, I return the counter. If it doesn't match a label, I return 0. Right? So I can give an estimate for everything. Okay, and the things that occur a lot, well, those are going to get a label at some point, and then those counters are going to go up. Right? And so I'll keep an estimate of those. And so then there's this idea of evicting something, and I want to do that without decrementing the counters. The space-saving algorithm, all it does is it does a swap on the smallest count. So it swaps the label on the smallest count without changing any of the counters. This gives an overcount, and it turns out it's a bounded overcount. Okay, well, let's not worry about that. Yeah.
You keep a decrement of how many times you decrement all the counters, and then when you want to know what the frequency of something in the cache is, you can bound the frequency between its count and its count plus the decrement.
Yeah, so this is actually, if you keep track of how many times you've decremented, and when you do a decrement, you decrement all the counters, keep track of how many times this actually bounds your error. Right, so good. So, then actually before we move on, let's just, the analysis is just this, right? How many times can we do a decrement? How many possible times can we do a decrement?
The number of unique elements minus the size of the cache.
So that's one bound, the number of unique elements that we can see. You can get a bound that way, but this isn't going to be the right bound.
The number of elements minus the cache size?
So that number of unique elements minus the cache size is going to be not as strong of a bound. You can do better.
The number of the total count minus the sum of the counts in of each element in the cache?
Minus the sum of each element in the cache. No, so it's not going to depend on the. So you can get a bound depending on the number of things not in the cache, but not based on something in the cache. There's something you could keep adding. Basically, there's one item you can keep seeing 90% of the time, right? And the more you see that, actually, the fewer times you actually do a decrement. So there's a way you can get a bound based on the things that you're not keeping track of, but not based on the things you can keep track of. So if I do a decrement, what I know is that there are k items which have a count greater than 0, of a count at least 1. And after I do that, I'm subtracting all k of them. Okay, so if this happens again, I need to refill all those counters. So every time I do a decrement, I'm decreasing my total count I've kept track of by k. So how many times am I able to subtract by k?
M over k.
Yeah, right. So the total number, this is the right analysis. So that total, so that total number of decrements is at most m over k, right? Because every time I decrement, I'm subtracting k things, and I must have seen that many things as many times. If I decrement more than m over k times, then my counters are all less than 0, and I know that's not possible, right? Because there are only m total things in the stream. M is the total size of the stream, and I can only decrement m over k times. And if I go back and look at my error bound, right, the frequency is off by at most m over k. Right? So this is basically the whole analysis. Right? There's a couple of things to keep track of, like, well, what happens if I didn't put something in yet, or I didn't account for something and something like that. The way to analyze this is to pretend you instead of use k minus 1 counters, but then analyze the case when you have k counters, but actually do this decrement whenever all of the counters become non-zero. So as soon as all the counters become non-zero, so that means I always have, I can always do this step, but then if after this it triggers them all become full, then I decrement everything by k. And then this analysis, if you work through this, it handles all the corner cases you could possibly think about. But, you know, this works. The total number of decrements is m over k, and that's exactly the bound we want. Right? So if I set k to be 100, I get 1% error on all the counts. And this is worst case bound. Right? It turns out you can't do any better than this in general. So this is the best you can do with this much space. Right? And the total space was k times log n times log m. Right? The number of counters and number of labels is k. All right, so kind of here's written out in a little bit more detail. Right, you keep a counter array, you keep a location array, and then you initialize all the counters and labels, kind of like in the majority thing. Right, and you do increments if you can. If something's 0, you replace it, and then if everything, if you don't have a spot for something, you have to decrement all the counters. Right, that's the whole algorithm right there. You have to implement this for your homework. Okay, so this shouldn't be too hard. The data here is just going to be kind of, I think, characters A through Z. So it's okay, yeah. Right, so this basically evicts if a counter gets down to 0, it's been evicted. Right, so it can be replaced by something else. It's kind of a soft evict. If I happen to see that element again, I can reuse the counter, but it's effectively evicted. And so this is always an underestimate. I never overestimate. I'm only increment the counter if it exactly matches the label, so I can't overestimate. Right? So this is going to get a bound that it's going to have that. So fj hat is always going to be less than or equal to the true count, and it's never going to be more than fj plus or minus m over k. Because this term is the total number of the is the total number of the decrements. Okay, and so if I kept track of the total number of decrements, I actually get a slightly better bound, right? It's actually between. It's never an overcount, and the undercount is off by most the total number of decrements. So if I actually keep a counter for that, I can say something a little bit better. Okay, so great. So this is the Misha-Gries algorithm, and so you're going to return a value fj hat, and you're basically going to have to answer questions. Did this item occur more than 15% of the time? Right? You're going to get it, if there are kind of 1,000 things in the stream, and it comes, and you see it, and your estimate is 18 times that I saw it. Right? Is that going to, did that element occur more than 50% of it? Or, sorry, your estimate is 180 out of 1,000. Did that element occur more than 15% of the time? All right, let's write this down. Okay, so let's say m equals 1,000, fj hat equals 180. So I have a question. Is fj greater than 0.15 times m? Greater than 15% of the time. Okay? What's the answer to this? I've seen some people mouth it and maybe, okay, so who thinks, okay, there are three possible answers, yes, no, and maybe. Okay, that's the truth, right? It could be. So who thinks yes? Who thinks no? Who thinks maybe? Okay, so the answer in this case is actually going to be yes. Okay, because this can never undercount, right? It never undercounts. I only decrement from this. Maybe I decremented 12 times. Then the true count would be 192, but I need it to be 150 in order to be over, right? So it's if I said this again, and I changed this number to 140, right? And let's say that k was equal to, let's say 100. Okay, so we can answer this question again with yes, no, and maybe. Who thinks yes? Okay, who thinks no? Who thinks maybe? Right, and the right answer is maybe. Right? It might occur more than 50% of the time. It might not. Okay, well, it's an approximation algorithm. We don't know the true answer, right? If this was 100, then it would be no. Right, so there's these no regions, maybe regions, and yes regions. Okay? And so with these approximation algorithms, you have to be able to interpret this yes, no, maybe situation. It's no longer just a yes or a no, it might be a maybe. Right? So with the majority algorithm, it's either yes, it's a majority, or maybe maybe this one is the most frequent item. Right? Or okay? Or it's a little weird on the majority issue. But this one, I can actually have these regions, yes, no, and maybe. but you're going to be given fj, and you're going to have to answer this. Okay, yeah.
Are there any real-time applications of this?
So versions of this algorithm have been deployed on routers to detect like denial of service attacks, right? So if a bunch of packets are going to a specific IP address, that probably means way more than would be normal, then it's kind of suspected that that a lot of people are trying to jam that IP address by sending all of packets there, and that's called this denial of service attack. So these things are deployed in this case, right? So this would be like a real-time application. You know, the most important things in like these models for like k-grams and bag of words is you're essentially keeping track of how many times these things occur. And the things that don't occur very often, you can kind of ignore. So you only need to keep the very frequent things. And so again, it's kind of a very similar model here, right? That's not necessarily a real-time thing, but there's kind of, if I wanted to do that in a stream and not keep track of everything, I can employ something like this. And then kind of there are versions of this. We'll see an extension of this to do dimensionality reduction, where we replace the counters with something kind of these vectors in some way. We'll explain. And then the count sketch version, which is not the count min, which we'll see next, but the count sketch version is basically used to take huge amounts of data and apply like a regression problem, and it compresses the data first, and then you can apply a regression problem on that. Right? And this is basically the kind of most of very large scale machine learning kind of when you have way more data than your model can handle, goes through something like that. It often compresses it through the count sketch first, and this is again a vectorized version of it, but then that's kind of the basis for dealing with, and also distributed machine learning and very large scale stuff kind of often goes through that mechanism. Okay. What do we talk about? Okay, so I want to talk now about a completely different way to do this. So the same problem, but I'm going to get an overcount instead of an undercount, and this is going to be randomized. Okay, so this is going to be called the count min sketch. Okay, and so now I'm going to keep k times t counters. Okay, and k, when you see k times t, what that's going to mean actually is I'm going to keep them in a table, essentially, or an array, where I'm going to set k this way. So it's going to be C11, C12, up to C1k, and then it's going to be C21 up to CT1 up to CTK. So I'm going to keep this T by K array of these counters. Okay, let me write actually T on this side. Okay, and I'm not going to keep any labels explicitly now. Okay, so this is one that's not going to keep any labels. Instead, I'm also going to keep T hash functions. Okay, and these hash functions are going to map from my domain to K. Okay, so I'm going to think of putting hash 1 here, hash 2 here, up to hash T here. Okay, I'm going to think of each hash function is going to correspond with one of these rows in the table. Okay? And so now, once I have this setup and the hash function stored, it turns out to store a hash function over a domain of size n is going to be roughly log n plus log m space. Okay, so kind of it's roughly that much space. Okay, the guarantees you need to worry about some other kind of some some weird issues here, but roughly it's log n plus log n space. So this is okay. So these are kind of replacing my labels in some way. Okay? And so now the algorithm here is going to be even simpler. So I'm going to have 4 AI in this string, or AJ. What I'm going to do is I'm going to then say for I in 1 to t, right? So I'm going to go through each row of this table. So each AJ, I'm going to send to each row of this table. I'm going to increment a particular counter, right? I'm going to increment counter I. And which counter am I going to increment? So I'm going to do an increment on this counter. And which one am I going to increment? I'm going to use my hash function to tell me. Right? So now I'm going to use the ith hash to increment. I'm going to hash the value j. All right? So I'm going to send this guy in, and it's going to map to this over to here, over to this spot, over to this spot, or over to this counter. Right? So each hash function is going to map to one of the counters, and it's going to increment that counter. Okay, and this is the whole algorithm right here. This is the whole sketch. So I'm just going to read through the items. I'm going to hash them in each one into the table. For each row, I'm going to hash it to a counter, and that counter gets incremented. Okay, and this is going to store all the information I need. Right, its size is now k, which will be small. It's going to be something like 1 over epsilon. I'm actually going to need k to be equals to be 2 over epsilon instead, where my epsilon is the percent error I get, and t is going to be basically log of 1 over delta, where I'm going to get a pack bound. It's going to be a randomized algorithm. These hash functions are drawn from a randomly drawn from a family of hash functions, and there'll be some probability of failure. This delta is my probability of failure. Okay, so think of this in practice. Someone might use, I think, 10. I think in our homework you're going to use 5 or something. And kind of the probability of failure is going to go down kind of exponentially as you increase t. Right? So it's 5 is pretty good. In production systems, 10 is the probability of failure is going down exponentially with that, so this is okay. Okay, and I need a factor 2 increase size here, 2 times 5. So maybe a factor of 10 increase in the size over the Misha-Green sketch. So this space here is going to be a little bit more. Okay, what I haven't told you how to do is how to retrieve. So now I want to think of doing a query. I want to do a query on an element q in n. And I want to return fq hat, right? So I want to return. So I have a query IP address, and now I want to return my estimate for the IP address. How do I get it out of this table? Right, this part is now a little bit trickier because I don't have a specific label associated with each potential query or 0. I have to do something a little bit more interesting here. Okay, so how would I get it out? How would I get this out of this table? I have a buffer.
Hash it and then average the counters in each row.
So close. So I want to do something where I want to return. I want to again access over all these i's hash function of q. Right. So I want to look at, for each value I, for each row of the table, I want to look at I want to hash this value q, and then I want to find the associated hash functions, right? So on a query, I'm going to find these counters in the query, right? So when I put in q, right, it's going to jump to these counters here, and averages is it's a reasonable guess, but that's not the best thing to do in this situation. There's something better I can do, and what? The min, right? The hint is in the name. Instead, I want to do a min over all values I, right? Because every counter is going to be an overcount, right? It has, I know every time q came into the table, I incremented the associated counters, but sometimes, like in the one up there, there's some overlap. So sometimes there's going to be an overcount, right? Just, right, when I have a hash collision, there's an overcount. But because they're always an overcount, each one is an overcount. The average will be an overcount, but the minimum is also an overcount. The minimum can never overcount, so I might as well take the smallest one, and that's going to be my best estimate. Turns out you can probably get some bound with the average, you can get a bound with the median, for instance, but the minimum was going to do better. Okay? I think if you took the median instead, you need an extra factor to rows of this table. The mean is a little bit harder to bound, but there are some bounds on if you use the mean here. But it's hard to do. The analysis is not as nice. Right, and I can do the min. Okay, so I know this is an overcount, so I'm going to get, and it turns out if I set the parameters like here, then I'm going to get the guarantee that fq hat is always going to be greater than the true value, and it's going to be less than the true value plus epsilon m with probability greater 1 minus delta. Right, so with the probability greater than 1 minus delta, right, then I'm going to get error at most epsilon m. So if this is if k is 200, right, then I'm going to get 1% error. Okay. Good. So now I can answer similar queries again. Let's say I run this algorithm, and you will run this algorithm on the homework. Again, once you have the hash functions, which you know how to do now, this is not hard. This is not hard to implement. Okay. Okay. So I told you this one wouldn't be too hard. But what you need to do is you're going to be given an FQ hat. Right? And you're going to have to answer, well, is this greater than 25%? Right? And it's a yes, no, or maybe. Right? And the homework kind of conditions on some probability, basically that I set that up so it should make sense if you use the 5 rows is what I tell you to use. So again, you have to answer yes, no, or maybe questions. And these are a little bit different than before, right? Because I can never undercount, but I might overcount. Yep.
So this doesn't give you the top list. It gives you the ability to answer how frequent any single one is.
Yeah. So if I want to now know which is the top one to do, if I just keep this, I basically need to go and check everything, right? In practice, what you can do is you can actually maintain Misha-Gree's summary on the side, where you keep track of those, and there's a way to do it, and it will. The thing I'm going to ask you next is why you'd want to do this instead of Misha-Gree's, and you can add it on in a way that maintains those guarantees. But so you can supplement a Misha-Gree's on here, and that will allow you to actually know which ones are the top. But this only gives you, by itself, it only gives you a day structure, so I don't explicitly know which ones are the best ones, unless I check everything. So that's one downside of this. So then what I just said I was going to ask, so why would I want to use this instead of the Misha-Gries summary? Right? It takes more space. I need k to be 2 over epsilon, and I have this extra log factor, and there's still some probability of failure. Right? And the overcount, undercount is not a big deal, because if I keep track of this, I can just add that on to all estimates, and that's the space-saving algorithm. Right? So it's not the overcount underestimate difference. There's something else nicer about this than the Misha-Gries algorithm. And I haven't said what that is yet, but
You don't throw away any of the data you do in the past algorithm. Like this matrix still represents every single data point we've seen, whereas my data points.
yeah, so it feels better in that I'm not throwing anything away. But it turns out the error guarantees aren't any better, right? I basically get this error guarantee. This is on the right-hand side, so the left-hand side, but I can add this to everything on the left-hand side. So actually, I don't get any better error guarantees. The count sketch will have an advantage like this, where is a version of this where I get the right expected value for everything. This is an overcount bias. Misha-Gries has an undercount bias, but this isn't solving that either. Yep.
I'm just thinking maybe your hash functions can provide some randomness, so it gives you some, I don't know, well, I guess you wouldn't want to run it multiple times, but just thinking there's something there.
Yeah, so think of the number of rows as you running it multiple times. So that's not really helping. Okay, so the issue is, what if I made a mistake? What if I accidentally added something that I shouldn't have? So in the Misha-Gries algorithm, like if there was instead of doing this, so what's a good? There's not a great router. I'm not sure what the router example of this would be. But let's say I'm doing this with I'm creating like the word count in some very large, like some large document. Let's say I'm doing it over the entire web, okay? And and I realize, so every web page I'm keeping some total word count, and I'm only keeping track of the top, like I'm keeping k equals to be like 100,000. Okay, so I don't want to keep track of all the weird strings. Maybe it's even 1 million. Okay, and so now I know someone updated one web page on the entire web. Okay, and maybe I have the old one cached, so I can say, let's take the old one out and put the new one in. With the Misha-Gries algorithm, there's nothing I can do. I can't subtract things from my situation. With the count min sketch, I can do that. I can actually subtract, right? If I want to subtract the effect of some web page, some word counts, I go back through and I hash to the counters and I just do a decrement. And then if I have new ones, I increment those back in. It still works. Because I've kept everything in there, right, I can subtract stuff I put in before. Okay, I can't subtract stuff. The guarantees won't work if I subtract stuff less than 0, but this works in what's called a turnstile turnstile model. Like if you go to the stadium for a football game, I don't know if I forget if they have these, but you often walk in to like a turnstile and it turns one crank, and then when you leave, you might walk back out again. So the frequency counts have to stay positive, and this is what the turnstile model refers to. So I can remove something that I added before, and the error guarantees still hold. But that was not the case with the Misha-Gries. Once I decrement something, I've lost information. Right? So the information is gone. I don't know what I've decremented. Once I remove a label, I do a decrement, it's hard to know that. Okay, but here it's all in there, so I can subtract it and I can add it back again. So this makes it what's called a so this is called a linear sketch. And so it means I'm essentially, with these hash functions apply some sort of linear function I'm putting on the data, and so I can, if I update the frequencies, I can just apply the same linear function. Right? So if I have a document where the word occurred 5 times in the document, I can do a +5 instead of a +1 5 times. Okay, so I can add and subtract in this model, and this makes it kind of more powerful in what it's keeping track of. And there are many situations where you want to do this even though it might have a factor of 10 or 20 in terms of space. Okay, so let's see. So let me, I didn't go through the analysis of this. I think I'm going to give you about like a 2 or 3 minute sketch of the analysis, and then I'll tell you the count sketch algorithm, which you won't have to implement, but I think it's worth knowing about this variant. And maybe I'll mention frequent item sets because I think that's in like the ACM handbook of what you're supposed to say in a data mining course, but for basically no other reasons. Okay. So, well, I mean, there's some uses of it, but it's okay. Okay. So the basic analysis here is that if I look at the expected number of overcount if I look at just one row of the table and I look at the expected overcount, right? I can look at a random. The expected overcount is basically going to be m over upper bound by m over k, because everything that's not the query Q, right? That has a total count of at most m. Everything that's not Q, and it's going to be distributed basically uniform across all of the columns. That's true for each row. Right, so those m and most m other things are basically distributed evenly because the hash function is deterministic once I pick it, right? So, but it's chosen at random, so those are distributed evenly. So the expected overcount is going to be m over k. Okay, which is going to be m over k is going to be m times epsilon over 2, right? So one half of as big as it needs to be. Okay, and so that means that I can apply what's called the Markov inequality, which says that the probability that my result is more than twice my expected value, which would be epsilon times m, is at most 1/2. Okay, so the probability I'm more than twice the expected value for a random variable that's greater than 0 is at most 1/2. And that's for one row, and if that's true for all rows, they're all greater than twice the expected value. That goes down exponentially, so the probability of failure goes down, it goes down exponentially. So if I set t equals to log 1 over delta, then this is log base 2. From the 1/2 to the power t is the probability that all of them are more than twice the expected value, which is epsilon. Okay, so it's kind of a 2-minute proof without writing anything down. There's some stuff in the notes, but basically it's a pretty cute proof, but it's not too hard. Okay, so I want to say the count. I'll tell you what the count sketch is, and then I will maybe I'll preview. I'll just kind of go over a couple of other things very quickly. Count sketch. It's basically going to be the same structure here. I'm going to have C11 up to C1k, up to CT1, up to CTK. So I'm going to have T times K counters. Then I'm also going to have these hash functions h1 up to ht. So I'm going to have t hash functions the same way as before. Now I'm going to add something else. I'm going to have t random sign hashes, right? So this is going to be a function. So this is going to be new. I'm going to have a function si. So I'm going to have t of these. Each one is going to go from the domain n to -1 or +1. Okay, so now the algorithm is going to be for a, j, and a, for I in 1 up to t. I'm going to do c of I, the ith hash function of j. This is going to be c of I, hi, j, plus si of j. Okay, so the difference here, I'm not always incrementing. I always add it or I always subtract it, every element here. Okay, so for every time a value j comes in, it's going to go into each of the hash functions, right? So if I have a j come in here, it's going to go to each of the hash functions. It's going to map to one of these things as one of the counters as before. And then it's going to do S1, S2, ST, right? It's going to either increment or decrement the same way. So for some rows, every time I see it, it's going to increment. For some rows, it's going to decrement. Okay, so I'm adding or subtracting, and then I can do a query on Q. Now my f q hat is going to be equal to the median over I of si of q times the counter of I of run out of space here. Si of q times the counter of I hash of q. Okay, so now I know whether I added or subtracted all of them to each counter, so now I'm going to undo that. If I added them, it's still a plus. If I minus it, I undo the plus. And then I'm going to get a bunch of these different values. I'm going to take the median now of these values. The advantage of this is that this is going to be an unbiased estimate. The expected value of fq of hat is going to be equal to f of q. So it's going to have the right expected value. It's going to have the property that fq hat minus fq, the difference between these is going to be at most epsilon times the second frequency moment. Okay, but I'm going to need to set, for this to be true, I'm going to need to set k to be about 1 over epsilon squared instead. And t is still going to be log 1 over delta. I think this needs to be 2 over delta because I'm taking the median. And the analysis is going to be somewhat similar, except I'll use a Chebyshev bound instead of a Markov bound. And I mentioned F2 is often much smaller, so even though K is bigger, this is often a win if there's an uneven distribution here. And it's the right expected value. So this turns out to be very powerful when I am trying to estimate the expected value of something. Well, my estimate is still the exact expected value. I know there's bounded error, and the expected value is still what it's supposed to be. So if I do enough of these, I'm going to get a better and better estimate, as opposed to some consistent bias that I can bound. Okay, so this is the count sketch. It's a little bit more tricky, but it has some other advantages. Okay, well, let me just mention the frequent item set problem. Okay, just for 2 minutes. Just bear with me. So now instead of a stream of individual items here, this is, so now my stream is T1, T2, up to Tm. So each element of the stream is going to be a set of items. So think of this like a receipt at the grocery store. 1 is milk, 2 is eggs, 3 is bread, something like this. Okay, and I'm looking at all these receipts, and now I want to find items like milk, which occurred many times, that occurred very frequently, but also pairs of items or triples of items which occurred very frequently together. Okay, and so there's like this old kind of story about data mining, which turned out that in the real data, it doesn't actually show up in real data, but the motivation was that these are grocery store receipts that diapers and beer would show up together on receipts a lot at the same time. I believe ACM obligates I tell this story as well, and so you can find that by they showing up on a lot of these receipts. Okay, and there's a famous algorithm called the a priori algorithm, and basically it means the main idea of the a priori algorithm is that if a pair of things, say diaper and beer, show up together at the same time a lot, then they must occur individually a lot also. So first thing I'm going to go through and say I want things that occur more than 25% of the time. I filter out each individual item on the first pass, which doesn't occur more than 25% of the time. And then I keep pairs of items which both occurred in the first set, and I make a second pass and filter again. And then I look for triples where all 3 of the pairs that make up that triple occurred more than that amount of time. And I can make multiple passes, but usually not too many, and this is a fairly efficient way of dealing with this. Okay, so that's basically that's basically the whole thing. So, and I usually go through this example, but you can see it in the notes, I guess. Okay, great. So I think you have enough to do your homework. I don't think it should be too hard, but let me know if you have questions on that.